Hello and clear skies, everyone, and welcome to York Observatory TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. I'm Quinton, and I'm joined tonight by Shannon, Matt, June, and Amin, and of course, our staff in the observatory, Anna and Professor Paul Delaney. We are broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. York TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. But if you can't make it to one of our broadcasts, don't worry. All of our TeleTube events are recorded and uploaded to our YouTube channel for you to watch at whatever time works for you. If you have any questions about the material covered in tonight's show, please feel free to ask them in the live chat and we will try our very best to answer them over the course of the night. If you have any questions or comments about our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle @York Observatory and on Facebook at Alan I. Carswell OBS. Last week's presentation was about some of the coldest environments that space has to offer, and so this week we'll be following up with a presentation about the hottest places in the universe. But before we get started with our main show, we want to give you a little update on what you can see this coming week. The moon is currently approaching the third quarter, following the wolf moon on January 28th. This is actually a better phase for performing lunar observations than a full moon, because the visible surface will be lit from the side, causing the surface features to be more visible thanks to the shadows they cast. The red planet Mars continues to be visible this week. Our viewers near the Toronto area will be able to see Mars high in the sky around sundown on clear nights, and it will continue to be visible until it sets in the west around 1 a.m. Above Mars in the sky are the Pleiades, a bright open star cluster commonly known as the Seven Sisters. Both Mars and the Pleiades are visible to the naked eye, but if you have a backyard telescope or even a pair of binoculars, you may be able to make out more detail. There are only 7 to 9 stars in the Pleiades that can be seen with the naked eye, but the cluster actually consists of thousands. If you have some equipment and a clear sky, why not try and see how many you can see? Or try and make out some of the surface features on Mars. If you have a telescope and live in an area with a dark sky, you may also be able to see Uranus setting around midnight this week. Now, fortunately for all of us, tonight the viewing conditions are very good. So I am actually going to hand the mic over, and we are going to share some live telescope images gathered with our very own 1-meter telescope for you all to admire before we get into the main meat of the show.
I thank you very much, Quentin. I'll just go ahead and start the screen swap now, if that's all right with you. And here we go. We're tuning in. This is Dr. Hyde. I'm just going to see if I can't transport us over to the 1-meter telescope here very, very quickly. And let's see here. I think we can do it. We are accessing the 1-meter telescope directly here for you all. So this is the 1-meter telescope that everyone can look at now. You are seeing what our telescope sees. So this is the 1-meter telescope at the Alan I. Carswell Observatory at York University. And this is our pride and joy, beautiful 1-meter telescope, a bit new. And we are looking at an absolutely fabulous object, which is, speaking of groups of stars, as Quentin mentioned earlier, we are fortunate enough to have two folks, Paul and Anna, at the telescope right now, moving it around for us. That's the telescope's control screen you can see on the left there. And we are pointed at the amazing object M38, I believe. Is that correct, Paul? That's a nice open cluster. Let me just make sure that you're loud enough here so everyone can hear you.
Hopefully. Nice crisp evening out here, but very, very clear, which is nice.
Indeed, it looks like we've got M38 coming through beautifully, very, very blue. I heard that the stars in M38 sometimes make out a shape for pi, but I'm not quite seeing it.
You've got to have a good imagination to see some of those asterisms, Elena, as you well know.
I do have a good imagination and a love of pie, but I'd have to say it's also known as the Starfish Cluster. So I'm gonna go ahead and say that maybe they're taking a bit of artistic license with this one.
Oh, absolutely, absolutely. But it is a youngish cluster, as are all open clusters. So in the grand scheme of things, this is probably only about 100 million years old. And of course, when we consider the age of our galaxy, or give or take a bit, 10 billion years, this is fresh off the block.
Indeed, and I believe we're going to be hearing a lot more about sort of hot things in this particular teletube, so we won't do too many spoilers. Now, let's see here. Quinton, you have a fun fact about M38?
Yes, I do. So as was mentioned, M38 is an open star cluster, much like the Pleiades. And in fact, there is another open star cluster located fairly close by in the sky. That is, of course, the star cluster NGC 1907. And what's interesting about those two star clusters is that even though they appear close together on the sky, astronomers believe that they're most likely just experiencing a flyby because they originated from very different parts of the galaxy. So they were not they did not come into being near each other. They're simply passing in front of each other, as it were.
That's absolutely fascinating. And I'll just call out that what you're seeing here is the live view through the eyepiece camera of the 1-meter telescope. So this is not necessarily what you would see if you took a lot of images and stacked them for astrophotography. This is what you would see if you were at our telescope looking through the eyepiece with your eyeball, pretty much. Depending on your vision, I suppose. And this is reading in live sort of continuously. You might be able to see it sort of blinking at the bottom. This is our Malin cam, and it is giving you pretty much as good of a view as we're going to be able to get for this object due to the wonderful seeing tonight. How are the skies, Paul?
Oh, they're absolutely fabulous at this point in time. It really is one of the clearest nights we've had so far this year. So I know we're only a little over a month into 2021, but this is a really crisp, clean evening at the moment.
Indeed, it's wonderful to have such a good seeing. Shannon, you had a fun fact and a little bit of information about the distance as well, right?
Yes, Professor Hyde. So I wanted to say that the cluster is actually 4,200 light years away from Earth, which means it's not really visible from the naked eye. As Professor Delaney said, it's a very young cluster. It's only 220 million years old, and has a radius of 25 light years.
Oh, that's a really, really good. And thank you very much, Shannon. That's great. And it is a very, very fun cluster to look at. We could probably stay and look for patterns in this cluster all night. As I said, some people saw a starfish. Some people saw the letter pi, the Greek pi. But if you look long enough, you could probably even see a piece of pie, or I don't know, your favorite video game character maybe. It's a wonderful cluster to start the night off with. And we have one or two other objects that we can try to go to tonight to give everyone a great show. And what would be greater than, of course, the planet Mars? Paul, yes, can we move to the planet Mars? Is that possible?
Sure, stand by.
All right, everyone, we are going to travel away over, well, actually much closer to the Earth. Travel through space at an incredible speed with our wonderful telescope. We're going to go to the planet Mars. And what you can see now is they're moving the telescope controls, searching for the planet Mars. And when the green, there we go. When the green circle gets onto the yellow circle, if you can see that happening now, that's how fast our telescope moves. So we
So stand by.
absolutely. So now that we've moved the telescope, we just have to get the dome out of the way. Our dome has a little slit, and the telescope has to look through that open slit or open door, if you will, out into the sky. And since we're pointed in a little bit of a different direction, Paul and Anna are out going to move the dome so that it lines up, and then we should be able to see the planet Mars. Now, we haven't put out a huge press release for it, but oh boy, is it bright. Let me lower that exposure time. Lower, lower, lower. We need a much lower exposure time for the planet Mars. There we go.
Okay, we're all free and clear with the dog.
Thank you very much. And I'm just messing with your exposure time at the moment.
Yeah, drag it down. We're at 4 seconds there for M38. We need fractions of a second for Mars.
Indeed, it is very, very bright still. Of course, we had our closest approach to Mars last year. Very, very exciting. There was actually a rather big event at the observatory for our Mars closest approach, if you might remember. And as we're decreasing the exposure time, we're sort of making it milliseconds instead of seconds here. The size shrinks down and we'll be able to see more surface features. So let me just increase this as well so we can increase our magnification, and we're still a bit bright. So let's take that down.
Hard to believe that Mars's opposition with us is over 4 months ago now. We're approaching, of course, our big event on February 18th with the landing of Perseverance.
I know. Well, and it's funny you should mention the 18th because I just want to give a little shout out. We do have an event planned for the observatory. So if anyone is interested in watching along with us for a little bit of a landing party on February 18th at 2:30 p.m., we are going to broadcast live on this very same YouTube channel, the Mars Perseverance landing. So we're going to have our own little observatory landing party. Everyone's invited. All right. I'm just going to mess with your settings here for a second, Paul, to increase our size a bit.
It looks as if we probably could have focused a touch better earlier in this evening. I'm sorry about that.
You know, it's a little baffling with the seeing being so good. Mars sometimes looks better with worse seeing. It's a strange effect. Now, let's see here. It looks like a couple of our crew have some fun Mars facts. Quinton, you want to go first?
Yes, thank you. So I wanted to say that in contrast to the rest of this presentation, which is going to be about very hot objects in the universe, Mars is quite a cold planet. The minimum temperature on Mars is the surface temperature on Mars is negative 143 degrees Celsius, and the mean or average temperature is negative 63 degrees Celsius, which is very, very cold. However, at its maximum, Mars can reach fairly reasonable temperatures for human habitation. The maximum surface temperature recorded on Mars is a balmy 35 degrees Celsius. So if you can visit around the right time, the conditions aren't actually that bad as long as you bring some sort of means of breathing.
Indeed, means of breathing is always super important. Atmospheric pressure being what it is, we are seeing a bit of a wiggle as Paul has mentioned. We are seeing might be just maybe our focus is just a little bit off. We're seeing a bit of a wiggle, but as you watch, we are getting this constant update in the image of Mars. You can just about make out that there are in fact surface features. So it's really quite fun.
Darker features towards the top of this image.
Yes, exactly. And we'll keep fiddling with it for a minute here and see if we can make those features pop out just a tiny bit more. And in the meantime, Shannon, you had a few fun Mars things to say?
Yeah, actually, surprisingly, Mars has the largest dust storms in the entire solar system. These storms can actually last for months and cover the entire planet. The Mars is actually home to the tallest mountain in the solar system. Olympus Mons, a shield volcano, is actually 21 kilometers high and 600 kilometers in diameter. So yeah,
Indeed,
hopefully.
Mars is a crazy place. Did you have any other fun Mars facts, Shannon?
Amin actually had one, so I'll give him the.
Oh yeah, let's go to Amin. Go ahead with your Mars fact, Amin.
Yeah, so far we found millions of cubic kilometers of ice on Mars, and it's actually enough to cover the whole planet to a depth of 35 meters.
That is an amazing fact. It's well, and is this carbon dioxide ice that you're meaning, or water ice?
I think all types of ice.
It's interesting to note that the poles of Mars actually have both kinds of ice, and it's one of the many, many ways in which we have found water on Mars. Which, of course, if you want to hear even more about Mars and all the fun Mars facts, make sure to come by on February 18th for our special broadcast. And in the meantime, we are watching it do a little bit of an atmosphere-inspired dance here.
If you give me a chance while you're chatting, give me the ability to do a little bit of focus tweaking. Let's see if I can just sort of leave. You've got the exposure pretty good. Let me see if I can tweak the focus just a bit.
Excellent. That sounds like a wonderful plan. All right. Well, while Paul is tweaking the focus a little bit, we can see that happening over to the left here. And what's actually happening is they're moving the telescope around, but not the pointing of the telescope. Actually, inside there are mirrors that reflect the light, which help it to, shall we say, magnify and bring that light through to the eyepiece. And by making small adjustments in position, we can actually do kind of a focus by changing the path length of that light. So that's what Paul is doing right now. And we're watching Mars kind of wiggle about at a reasonable speed here. But if we might see it poke through a little bit more sharply. And as we're watching this, just keep in mind what we said about earlier. There is that just a hint of that darker region up on the top of the what we see as the top, I should say, of Mars, and that would be what's called an albedo region of Mars. Oh, there we go. That's the wrong way to focus. So if you ever wanted to blow up a planet, this is how you do it safely. You cause it to blow into a ring by changing the focus. So we're doing a little playing with our optics. Quinton, do you want to talk about another fun Mars thing?
Yes, I'd love to. Mars is the only rocky planet in the only rocky object that is still classified as a planet in the solar system that has more than one moon. Mars has, of course, two moons, Phobos and Deimos, who I believe are named after the Greek gods of fear and terror, which are considered to be separate concepts in the tradition. And those are, of course, very small. They're basically just captured asteroids from the asteroid belt. Now, Mars is located fairly close to the asteroid belt. Its orbit is the last planetary orbit before you reach the asteroid belt, which stretches between the orbits of Mars and Jupiter. And these are both asteroids which have, through some sort of fortunate or unfortunate coincidence, happened close enough to Mars that they've ended up in its orbit for a long period of time. And the reason why we only see small asteroids in Mars's orbit is because it's actually quite rare for rocky inner planets to have moons. Objects like Jupiter and Saturn and the other gas giants, of course, have many moons, dozens of them. But neither Mercury nor Venus has a moon, and Earth, with its large moon, is very much an outlier, which we believe that we owe a debt of gratitude for, because without the tidal influence of the moon on the early Earth, it would have been much more difficult for life to form here. So Earth is special in a lot of ways, and one of those important ways is the fact that our moon is of such large comparative size compared to the host planet.
Indeed, it is wonderful to have our large moon, and Mars's moons being, potentially captured asteroids. It does actually mean that those strange little moons are not entirely as stable as one might hope for, and in particular, are thought to perhaps collide with the planet at some point. Not terribly, not in the terribly near future, but might not be there forever. And in fact, if they are approached in a way such that they can be broken up, we might even have rings around our next planet. So we can see that the image is getting clearer and clearer as Paul continues to focus, but we are still getting a bit of a wobble from the atmosphere. And we will continue on here. So Mars is, I don't know, Paul, is that about as good as we can focus it? I think.
I suspect it is, but I'm continuing to fiddle here. Of course, the stability of the atmosphere is not helping us any, but we're probably as close as we're going to get.
All right, so we'll go ahead and I think this is probably a good point to say we've probably in the middle of these wiggles gotten as good of an image as we can get for Mars. So let's go ahead and pick our best guess for the focus. And we'll start thinking about where else we might want to go in the sky. In fact, Mars, as was mentioned before, is of course very, very, very cold. A little bit off topic for this particular week's TeleTube. A few folks were wondering if we can perhaps look at something a little bit hotter, maybe even the Andromeda Galaxy.
Well, do you want to try the Andromeda Galaxy, or would you like to pop over to M42? Both are in the neighborhood, shall we say?
All right, let's open that up as a question in the chat. Andromeda Galaxy or M42, you say? All right, well, the Andromeda Galaxy, as some of you may know, just so you can take your best pick, the Andromeda Galaxy is the closest full galaxy to the Milky Way. It is thought to perhaps collide with the Milky Way at some point. And, in the very, very distant future, it's also thought to be very similar to the Milky Way in its general size and shape. Now, compare that with M42, and M42 is also known as the Orion Nebula, and that is inside our own Milky Way galaxy. So let's just see if anybody has voted. M42 or Andromeda. And we'll just see if anyone wants to vote in chat. And just as a little shout out, as mentioned by Quinton, if we did go to Andromeda, we could talk about AGNs, but M42 might be brighter. So a few people, there's a little bit of a dual, I suppose, option here. They both sound amazing, but if we have to pick, and we got 2 votes in chat for Andromeda. So I think Andromeda is winning in chat. Any votes for M42? And
we've got time to go to both of them anyway.
Yes, exactly. So let's try Andromeda, please, Paul.
M31, stand by.
All right, we are trying to go to the Andromeda Galaxy, leaving the Milky Way. Very, very exciting, and Paul is trying to move us there now. So it's as you can see, it also has an M number, and just in case anybody hasn't encountered these before, these M's are Messier numbers, and this was a list of Messier objects, which were a bunch of things that were not comets and were annoying somebody who was trying to find comets. So he made a list, and it turns out there are all kinds of different objects. So M31 is the Andromeda Galaxy. And this is a fairly large object, but it can be very hard to make out. So like last time, we're also going to have to move the dome. And we'll see what we can see here. Fingers and toes crossed. Are we aligned in the dome?
We are.
All right.
Exposure time a little.
Yep, let me just, so this will be a fainter object. We're changing the exposure time accordingly to a very high level, as you can see. I don't think I could overexpose this. So we're just working on the Andromeda Galaxy, And we'll see what we can pick out here, if we can get it. And let me actually zoom out because this is a large object. So this is looking better. So we're pointed at the galaxy, huh?
Yeah. Although I agree with you, that looks a little odd, doesn't it?
It's we are having a little bit of trouble determining which part's the galaxy here. So we're definitely pointed in the right direction.
Yep,
M31. And our exposure time is still not quite high enough. So let me turn up the gain a bit, not too high, just to bring out some contrast. And I'm going to go ahead and adjust my white balance here a little as well. Let's see if I can pick out a smidge of detail.
That's very disconcerting. I do not see the bulge of Andromeda there at all. Now, that's very odd.
Well, we are trying to go. We are trying to go to another galaxy. That's not always easy. I mean, so far we haven't really managed to explain our own galaxy all that well. So another galaxy might be a bit of a far fetch. But let's go ahead and check the current telescope position. Actually, so Andromeda. One way we can check this is actually to just check the coordinates of Andromeda Galaxy against where we are.
Well, we're definitely not there. Stand by.
All right, so that might be the problem. Our RAN deck were not quite correct, so we were pointed in an interesting place, but maybe not exactly the right place. We don't want to miss our galaxy here. All righty.
That's okay. We were not in the right place.
Don't we were just lost in space for a moment, as can happen. So if you do get lost in space, I always advise to have a very good spaceship handy, and there's no spaceship better than our 1 meter telescope. All right, so we were just, as you can see, in the opposite direction. So they need to reorient the dome, and then we will see what we can see. And I have already turned up the exposure time in anticipation of hoping to catch this neighbor galaxy. All right, so as we are traveling over, oh, what is this we see? This is starting to look good. Oh my goodness, everyone. This is amazing. This is the best I have ever seen it look through Malin Cam. I am super impressed. As soon as somebody else starts talking, I'm going to take a screenshot of this. I'm so happy. Yep. All right, it does look amazing. Quinton, do you want to chime in real quick for a very, very, very fast little galaxy fact?
Yeah, I would love to. So as I agree, this is the best that I have seen the Andromeda Galaxy through the telescope. Now, this bright spot is not the entirety of the galaxy. This is just the nucleus of it. The rest of the Andromeda is, of course, it has a big spiral shape, much like the Milky Way itself does. And if we had a longer exposure time and perhaps a more efficient camera, we would be able to see all of that. But the nucleus of the galaxy is so bright because, like pretty much all galaxies, there is a supermassive black hole at the center. And what is happening near that black hole is there is a huge amount of infalling matter, which is getting sucked into the black hole, and it is being compressed so much as it falls that its own friction heats it up and causes it to glow very brightly. This is called an active galactic nucleus, and we will discuss it in a lot more detail later in the presentation. The Milky Way galaxy, of course, also has an active galactic nucleus, and they are some of the brightest objects in the universe.
That's amazing. And it is so exciting to see the Andromeda Galaxy. We wish we could show you objects all night, but we actually have a really wonderful show planned. So Quinton, I'm going to probably hand it back to you for our regular planned show. And we'll have to say goodbye to Professor Delaney here shortly and Anna. And as you're busy getting that transfer set up of the screen share, I'll just say thank you very much, Professor Delaney and Anna. We're handing over the screen back to Quinton and the crew now. And thanks a lot for joining tonight.
Yeah, thank you very much. All right, thank you very much, everybody. So with that said, we are going to dive into this week's literal hot topic. I am going to hand the mic over to Shannon, and she will get us started.
Well, hello everyone. Thank you for joining us. Today we have a very scorching topic, extreme hot environments in the universe. There are many extremely hot environments in our universe. In our solar system alone, we have planetary objects that exhibit a great amount of heat. Venus and Mercury are the hottest planets in our solar system. Venus is the hottest planet and the second closest to the sun. You may be wondering, why isn't Mercury the hottest planet in the solar system if it is the closest planet to the sun? Well, Venus has a thick and a very toxic atmosphere that is made up of primarily carbon dioxide. Within the atmosphere, there are also thick clouds of sulfuric acid, which helps to insulate the planet and is responsible for the high temperatures. Venus has a surface temperature of 465 degrees Celsius. This is so hot that it could melt lead. Its neighbor Mercury is very hot as well, but only during the day. Due to the fact that Mercury is the closest planet to the sun, it receives 7 times more light than that of Earth. However, Mercury only has a thin atmosphere, so while temperatures in the day can reach a maximum of 430 degrees Celsius, this heat quickly dissipates at nighttime. Without an insulating blanket of gas around the planet, causing the temperature to plunge all the way down to negative 180 degrees Celsius. The sun is the main heat source in our solar system. The sun is made up of 92.1% hydrogen and 7.8% helium. This means that the sun is essentially a hot ball of gas that's held together by its own gravity. There's nuclear fusion at the core of the sun, which heats it up to a temperature of 15 million degrees Celsius. Nuclear fusion is a process where hydrogen atoms become compressed by a great amount of pressure. They then become fused together, which creates helium. Nuclear fusion produces a great amount of energy. Immediately after being released from the core, solar radiation enters a layer of the sun called the radiative zone. This region is so dense that the light cannot escape immediately. Rather, it will bounce around this layer for 1 million years on average, before eventually moving to the convective zone. The convective zone is the upper layer of the interior of the sun. In this layer, the temperature is 2 million degrees Celsius. Beyond this convective zone is the photosphere, which is the layer where the sun's radiation can be seen as visible light. This layer can reach temperatures as high as 5,500 degrees Celsius. The sunspots on this layer are much darker and cooler than the rest of the layer. The temperature of the sunspots is 4,000 degrees Celsius. The next layer is the chromosphere, which is cooler than the photosphere layer. However, in contrast to the photosphere, visible light is very weak in this layer. In truth, it can only be seen during total solar eclipse, where the moon completely covers the photosphere, where the chromosphere can be seen as a red ring around the sun. The final and the hottest layer is the corona. Now, you may be expecting the outermost layer to be the coolest. However, temperatures here actually range from 1 million degrees Celsius to more than 10 million degrees Celsius. Solar missions such as NASA's Solar and Heliospheric Observatory, SOHO, continue to explore why the corona is the hottest layer. With all this in mind, it is evident that the sun is very large and hot, yet it's not as large or as hot when you compare with other types of stars. Stars are responsible for the great amounts of heavier elements in galaxies, as they release these elements when they die. Stars are predicted to form from spinning clouds of gas and dust that collapse and break up into two or more blobs. As a cloud collapses, the material in the center begins to heat up. The center is known as a protostar, which will over time become a star when enough pressure is generated in the core to start the process of nuclear fusion. Our sun will stay in this mature phase for about 10 billion years. However, very large stars, which are 100 or more times larger than our sun, known as hypergiants, will have a lifespan of only a few million years. These hypergiants are much hotter and will have a lot more energy than our sun. For example, the surface temperature of these hypergiants could exceed 30,000 degrees Celsius. These hypergiants are very rare in the universe currently. However, it is predicted that these stars were common when the universe was younger. Most of these early hypergiants have since died, since in general, larger stars tend to have a shorter lifespan. There are actually many different types of stars that vary in size, temperature, and energy. For example, protostars, main sequence stars, red giant stars, white dwarf stars, red dwarf stars, neutron stars, and supergiant stars. Main sequence stars are the majority in our galaxy. Our sun is a main sequence star, and these stars can vary in size, mass, and brightness. So, what makes them common? Well, these stars do all the same things. They undergo nuclear fusion at their cores, which releases a great amount of energy. The mass can vary from 0.08 times the mass of the sun to 100 times the mass of the sun. When the star is unable to continue a fusion reaction at its core due to a lack of oxygen, the star will leave the main sequence. Although what happens next depends on its mass. I'll now hand it over to Matt to discuss some of the more dramatic fates for a star going supernova.
Well, thank you, Shannon, for that interesting explanation about stars and how hot they can get. But what about the death of a star? Would that be hotter than the actual star? Well, in order to figure that out, first we should mention what happens at the end of a star. You see, there are different types of explosions that can happen in the universe due to a star, not only lighting up in the sky in such a fascinating way, but also making it hotter than we can imagine. Type 1A supernovae are thought to be the result of the explosion of a carbon-oxygen white dwarf in a binary system, resulting from extreme density, not temperature by the way, once the Chandrasekhar limit mass is exceeded. They are the brightest of all supernovae and can outshine an entire galaxy at their peak brightness. This supernovae can get as hot as 3.44 billion degrees Celsius in less than 1.2 seconds after exploding. Type 1A supernova events can create temperatures ranging from 4 to 36 billion degrees Celsius, depending on the physical parameters of the white dwarfs. So far, this is just getting hotter and hotter. Now, we have seen what happens to a certain type of regular size type of star, we could say. However, for a much larger star, let's say 25 times the mass of the sun, it would be massive enough to create temperatures and pressures needed to cause the carbon in the core to begin to fuse when the star contracts at the end of the helium burning stage. The cores of these massive stars become layered like onions, like we see on the image on the right, as progressively heavier atomic nuclei build up in the center where the temperature is approximately 300 million degrees Celsius, once the thermonuclear process with helium starts. As a star this massive evolves, it undergoes repeated stages where the fusion in the core stops and the core collapses until the pressure and temperature are sufficient to begin the next state of fusion, reigniting to halt collapse. When the core's mass exceeds a certain limit, the process can no longer continue and the catastrophic collapse ensues. The outer part of the core reaches velocities of up to 23% of the speed of light, which is extremely fast, by the way, as it collapses towards the center of the star. For type 2 supernovae, the collapse is eventually halted and the falling matter rebounds, producing a shock wave that propagates outward. The energy from this shock frees heavy elements from the core. And in the typical type 2 supernova, the newly formed neutron core has an initial temperature of about 100 billion degrees Celsius, which means it's 10,000 times the temperature of the sun's core. Much of this thermal energy must be shed for a stable neutron star to form. Otherwise, the neutrons would boil away. Well, have you wondered what happened? What would happen if these newly formed neutron stars collapse and form another explosion? Well, as a matter of fact, that has actually happened, and it's a really interesting phenomenon called kilonova. A kilonova is an astronomical event that occurs when these two neutron stars, or a neutron star and a black hole also, merge into each other. The temperature in this process can go up to 1 billion degrees, and not only that, but the actual explosion occurring in the kilonova is even stronger than the normal supernova I already mentioned. But we can distinguish this type of explosions not only from that, but because of its faster time of evolution, the fainter absolute magnitudes, and redder colors. Well, now that we know explosions are really hot, what about bigger objects? John will help us on that.
Uh, Thanks. Very interesting, Matt. Let's scale up a little bit from the individual stellar events to consider galaxies, which contain hundreds of billions to trillions of stars. Supernova, like supernova 1987A, heat up and contribute fresh, hot, energetic material to the interstellar medium. The blast wave from SN 1987A is hurtling material into the interstellar medium at 4% of the speed of light. The interstellar medium, or ISM, is the radiation and matter, primarily hydrogen and helium, that occupy space between star systems. It can be as cold as 260 degrees Celsius or reach temperatures up to a spicy 10 million degrees Celsius. Events such as SN 1987A help cycle the material in the interstellar medium. And like an influx of extragalactic gas, it can trigger an active galactic nucleus, or AGN. What is an AGN, you may ask? An active galactic nucleus is when a supermassive black hole, like that of which we believe resides in the center of all major galaxies, becomes active due to infalling material. The supermassive black hole forms a disk of matter that it's accreting, which follows a decaying orbit into the black hole itself. This is known as an accretion disk. The accretion disk gets super hot due to the high speeds of infalling matter and the friction between this matter. The AGNs are so hot that they can even emit X-ray light. And the blackbody radiation expelled from them is the most luminous, persistent electromagnetic radiation sources in the universe. It's so bright that it allows us to see young galaxies forming and accreting mass in the early universe. But not all of this accreted mass stays in the galaxy, or falls into the black hole for that matter. Including AGNs, there are a few thermal methods which can shed the interstellar mass of a galaxy. In the AGN, the temperature is so hot and the kinetic energy of the gas is moving at the near speed of light, and the immense angular momentum due to orbiting such a massive body at these speeds, the AGNs form a hot, energetic beam or jets of matter moving at relativistic speeds away from the poles of the supermassive black hole. These jets can stretch out for thousands or even hundreds of thousands of light years, stretching even further than the host galaxies themselves. The speed of the hot material in these jets can exceed 99.995% the speed of light. These outflows have the capacity of heating the interstellar medium to 100,000 degrees Celsius, or even up to 1,000,000 or 10 million degrees Celsius. It may also strip large amounts of gas from the interstellar medium and inhibit star formation in the galaxy through a feedback mechanism, which eventually sees the hot gas return to the galaxy like throwing a ball in the air. Eventually, gravity brings it back and the cycle can repeat itself. Here at home in the Milky Way, we see a similar structure bubbling out from our galactic core. These bubbles of hot gas are more than 1,000,000 times more energetic than that of the supernova and are moving faster than 1,000 kilometers a second. It stretches over 50,000 light years, or about half the diameter of the Milky Way itself. Research suggests that these bubbles were formed not by an active galactic nucleus, but instead generations of supernova explosions. These outflow bubbles influence the galaxy's interstellar medium and the magnetic field, and may even promote star formation. On a larger scale, galaxy groups, known as clusters, grow hotter and larger by pulling stray galaxies towards them. The hot energetic gas between the cluster galaxies is known as the intergalactic or intercluster medium, similar to the interstellar medium. Through a process known as ram pressure stripping, the intercluster medium drags on the interstellar medium of an infalling galaxy, causing a tail of hot gas to trail that galaxy as it passes through the cluster. The trailing gas is heated and compressed, causing a burst of star formation, and resulting in the galaxies taking on a jellyfish-like appearance, which earns them the title jellyfish galaxies. Now on to Amin, who will be taking us to even larger scales.
Thank you, June. In the early 1900s, Edwin Hubble discovered that not only were there many galaxies outside of the Milky Way, but that most of them are receding from the Milky Way. This meant that the universe is expanding. If the universe is indeed expanding, then if you rewind time, the universe must have been smaller before. You might continue to rewind until the observable universe shrinks and shrinks all the way to a single point called a singularity. This idea led to the Big Bang theory, where the universe expanded out from this point. The Big Bang model does not actually describe how the universe started, as that is still unknown, but it does tell us about the first stages of our universe. In the first fraction of a second, called the Planck epoch, we have no idea what the universe would look like, because the size of the universe is smaller than the smallest length that makes sense to us. More on that later. The temperature at this stage is over 10 to the 32 degrees Celsius, which is a number with 32 zeros. After this, the fundamental forces of nature emerged. Gravity, the electromagnetic force, and then the weak and strong forces emerged, in that order. Inflation began around this time too, which is a theorized massive acceleration in the expansion of the universe, which soon ended but had a massive impact on the structure of the universe as we know it today. The temperature during that period is 10 to the 28 degrees to 10 to the 22 degrees Celsius. Several epochs follow, where the first particles started to form. Temperatures begin to cool as the universe expands. By the time the first atoms form, the temperature of the universe has dropped to 4,000 Kelvin. The cosmic microwave background radiation was emitted at the point where the universe expanded enough to allow light to be released. Eventually, larger structures in the universe came together, such as the first stars and galaxies. In the next slide, I'll discuss the Planck Units in more detail. The Planck Units were proposed in 1899 by the German physicist Max Planck. The Planck length is the smallest length in the universe, which makes sense with our current models. It is equal to 1.6 times 10 to the minus 35 meters, which is a really small number with 35 decimal places. It is much smaller than even the smallest of particles. The size of the Planck length can be visualized as follows. If a particle or dot about 0.1 millimeters in size, the diameter of a human hair, were magnified in size to be as large as the observable universe, then inside the universe-sized dot, the Planck length would be roughly the size of an actual 0.1 millimeter dot. Below this length, if you tried to measure something, you would interact with it and create a black hole. Lacking a theory of quantum gravity, we do not know if the Planck length is the actual limit, but it is the limit using our current laws of physics. The Planck time is a related quantity, and is the time a photon traveling at the speed of light would take to travel one Planck length, making it the smallest period of time that makes sense. The Planck temperature is the theoretical highest possible temperature, also known as absolute hot. It is equal to 1.4 times 10 to the 32 degrees Celsius, which is the temperature in the earliest fraction of a second after the Big Bang. This temperature is the point where a black body, an object that absorbs all light and emits only heat radiation, would emit radiation with a wavelength of the Planck length. Before stars and planets formed, hydrogen plasma filled the universe, which trapped radiation inside what can be described as superparticles. As the universe expanded, the plasma and radiation also cooled. Eventually, protons and electrons were able to combine into hydrogen atoms in what is called a recombination epoch. Once this happened, photons, or particles of light, could suddenly travel freely instead of being trapped. This resulted in a mass release of photons everywhere in the universe. We can still see this radiation, but by now its wavelength has been stretched so much from the expansion of the universe that it has become microwaves, and its temperature is just 2.7 Kelvin, which is just above 0 Kelvin or absolute zero, the lowest possible temperature. As an aside, in Celsius, absolute zero is negative 273.15 degrees. The cosmic microwave background is one of the biggest pieces of evidence of the Big Bang model, especially because we can see it everywhere we look. Originally, it had a massive temperature of 273 million degrees Celsius, but as with all things, it cooled due to the expansion of the universe. Particle accelerators can help recreate large temperatures like those of the early universe, and also the types of matter that existed then. The largest particle accelerator we have is the Large Hadron Collider, which is a circular tunnel of 26.7 kilometers circumference. It can generate temperatures a million times hotter than the sun. To probe the Big Bang further, we would need a machine so large that it would probably have to be based in space. Great discoveries will be made in this field in the future. Well, everyone, you have been listening to the Allen I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends at York University. The hosts this evening have been Quinton, Shannon, Matt, June, and myself, Amin. Our live observers have been Anna and Professor Paul Delaney. Make sure to leave any comments or questions in the comments section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory and check out our website for show notes, content updates, and contact info at observatory.info.yorku.ca. Thank you for tuning in. Clear skies and have a good night.
Well, it really is crazy to think about the fact that stars can heat the universe up to such a hot temperature. They can heat the interstellar medium from its like minimum temperature of negative 260 degrees Celsius all the way up to tens of thousands or even millions of degrees Celsius, just when they explode at the end of their lives, when they run out of hydrogen to burn. There really is a lot of very interesting, very hot places in the universe, and thank you all for tuning in tonight to explore some of them with us. Have a good night.